So we don't really have anything to do today. 6.9 in the text is worth reading. I think it's 2 or 3 pages max. Give it a read. It's geometry. I believe they say in the real world. I like to think of this as of the real world. And it's really just sort of a conclusion to everything we've done so far. The real question is what is the geometry of the universe? All right, and back in the 16, 17, 1800s, before non-Euclidean geometry was really studied and accepted, it was widely viewed, pretty much pushed pretty hard by Immanuel Kant, that the only true geometry is Euclidean geometry. It's the geometry we perceive around us, therefore it's the geometry of the universe, therefore it can be the only geometry, right? So Immanuel Kant says, because we perceive our world as Euclidean, it is Euclidean. And this was very pervasive. It's sort of why non-Euclidean geometry took so long to come along, is because sort of suggesting anything other than this was sort of heresy. But then, of course, we have Gauss, right? We have Gauss comes along, and I don't really want to give him credit for coming up with hyperbolic geometry. I really sort of like Lobachevsky and Bolyai. But Gauss comes along, and he knows that that if the world is non-Euclidean, then you can look at triangles. You can measure the angle sum of triangles, and if you get something other than 180, if you get an angle sum less than 180, then you're in hyperbolic geometry. And if you get an angle sum bigger than 180, then you're in elliptic geometry, right? So he measures the angle sum of a triangle consisting of the tops of 3 different mountains. 3 mountains, I think, somewhere in the Alps. So measures the angle sum of a triangle formed by the peaks of 3 mountains. Right, obviously, if you're going to sort of look for an angle sum other than 180, you need a really large triangle to look at. So he goes with peaks of 3 mountains, and what's his result? Depending on where you look, I've actually read 2 different things. I've read that he found exactly 180. I believe our textbook says he got something other than 180. It doesn't really matter. It's about 180. But sort of meaningless. Why? Because there's errors in measurement, and the only way you can conclude it's Euclidean is if you have exactly 180 with 0 error in measurement, right? Anything less or anything more, and it's inconclusive. So, but this is still inconclusive. Because of errors in measurement. Right, if I get 179.99, well, unfortunately that's still an inconclusive result, right? It's because of errors in measurement, this is never really going to do anything for us. And our textbook claims that this is what he was trying to do. We know he did measure these angle sums, and our textbook claims he was trying to sort of answer this question of what is the geometry of the universe. I believe in the lore, this is sort of what people usually say, and this is what our textbook goes with. My understanding is that that's probably not true. There's lots of biographies written on Gauss, and most people reject that he was measuring these angle sums in an attempt to answer this question. And to me, the most pervasive argument against it is because if he thought that a triangle across the peaks of three mountains was large enough to observe any sort of difference between the angle sums here, well, that's not a very large triangle at all. If our universe was sufficiently curved so that a triangle this small would be enough to observe a difference between the angle sums of 180 and some sort of positive defect, well, the moment you look out into the stars, into the universe, into the night sky, you would observe that there's some really weird stuff going on. It would not look Euclidean. This is way too small of a triangle. So our textbook says this is what he's trying to do. Probably not. But Lobachevsky did really want to do this. And he suggests taking a triangle across, I believe it's a star, I think it might be Alpha Centauri or something, and the position of the Earth on two different sides of the sun, so 6 months apart. But he wants to, I don't know if he actually attempted this or just suggested doing it, so I'll say suggested. But he suggested astronomical measurements of triangles, we'll just say between stars. So I don't know if he actually did this or just suggested it. It has been done, of course. We've taken very large triangles across stars, and we get 180 degrees. So there's that. And Poincaré really says, who cares? Like, it doesn't matter. All three of these geometries are sort of cool and interesting in their own right. You know, in our normal world, in the world we live in, that we perceive around us, it looks Euclidean. Once you extend to looking at us on the Earth, though, now spherical geometry seems to be the right one. So they all have their uses. But in comes relativity. Oops. And let me preface this with something about surfaces of constant curvature. So this isn't really relativity right now, this is just differential geometry. But surfaces of constant curvature. So you really just have three of them. If you have positive constant curvature, positive, you can always rescale it to just equal 1. Then your surface basically is a sphere. It looks like a sphere. If your curvature is 0, then the surface you're looking at looks like a plane. It's a flat Euclidean plane. Flat, spherical. Or you have negative constant curvature. Negative constant curvature looks like a saddle. All right, so one of those things that you've seen before in Calculus 3. So this is negative, and we say these are hyperbolic surfaces. Why? Because each one naturally admits a geometry, and the natural geometry of one of these, of positive constant curvature surface, is spherical, it's elliptic. The natural geometry on a plane is Euclidean, and the natural geometry on one of these surfaces of negative constant curvature again, you can rescale this always be -1, is hyperbolic geometry. Almost all surfaces are of the hyperbolic kind. Almost all surfaces are hyperbolic. What I mean by that is if you reach into a bag of all surfaces of constant curvature and you pull out one, the probability that you pull out one of these is 1. Right? So almost all surfaces are hyperbolic. And relativity allows for the universe to not be flat. Relativity allows for the universe to be one of these other surfaces, to allow it to either sort of admit hyperbolic geometry or elliptic geometry. And it actually says, it actually tells us what needs to happen for each of these things to occur. So what you can do is we've got this ratio, I believe it's usually called omega, and it's the ratio of the average density of the universe so this is measured. We can measure this. I have no idea how physicists measure this, but this is measured. Over it's the critical energy density. And critical energy density is the mass of the universe required, or the density of the universe required to make it flat. All right, so density needed. Density needed for the universe to be flat. In other words, Euclidean. All right, so relativity computes this number. It gives us this number, says, all right, this is the critical energy density, this is how much we need to observe for the universe to be flat, and we've gone out and we've actually measured, all right, the average density of the universe. So of course, this means that if this ratio is 1, well then, the average density of the universe is the critical energy density, and the universe is flat. Then the universe is flat. If it's bigger than 1, then it has positive constant curvature. I haven't done omega in a long time. These are bad. If omega is bigger than 1, then positive constant curvature. And if this ratio omega is less than 1, then we have negative constant curvature. So like I said, average density of the universe, this is measured, this has been measured, and the results, they got omega is 1. All right, so average density of the universe has been measured or computed, and we find that omega is 1. Does that mean the universe is flat? It's Euclidean? Well, unfortunately, once again, you can't conclude that. There's always errors in measurement. Unless you have 0 error in measurement, and you get this is exactly 1, then yes, you can conclude it. But there's always going to be errors in measurement, and that means you can't really conclude it. So what do I want to say? What this means, though, is even though it's not entirely 100% conclusive that the universe is flat, because the area of measurement here is pretty small, what you can say is that it's at least nearly flat, right? So it doesn't look almost flat. So this implies that the universe is at least nearly flat. And by the way, thinking in terms of area, when I say at least nearly flat, what does this mean? Well, if it's hyperbolic or if it's elliptic, remember to measure the area of a triangle, in hyperbolic geometry it's k times the defect, in elliptic it's k times the excess. When I say at least nearly flat, that would mean that even if you take very, very large triangles, very, very large area, the defect or the excess is very small. So in order to have a large area but a very small defect or excess, that means that scaling factor k has to be huge, right? So when I say the universe is at least nearly flat, if it's not, so if not, then k is very huge. So that's it. That's basically the whole section. There's a really nice summary in this chapter, by the way, or in this section. A nice summary of the comparison of the results of the differences between the two geometries. A table that summarizes all these things. It's pretty cool. But that's the whole section, and we're done with geometry 2. So you're not leaving this class as an expert in hyperbolic geometry or an expert in elliptic geometry. But what I hope you have gotten out of this class, if nothing else, is sort of an idea behind how math works, right? These axiomatic systems. You axiomatize something, and then you see what you can prove from there. And as an axiomatic system, at the very least, hyperbolic geometry is real. It exists. And because the universe is allowed to be hyperbolic, it's not necessarily just a mathematical abstraction, right? These things do occur. How about the final exam? Let's see if you're thinking about the final exam. When is it?
Wednesday.
Wednesday. What time? Yeah, I'm 99% sure it's 2:15. So this is Wednesday at 2:15. There's an announcement on campus. So that gives us some time from now until then for the exam. It's 2 hours long. Our typical exams are only 50 minutes. But despite that, I'm not going to make an exam twice as long as the usual one. So it's either going to be 5 or 6 problems, meaning either the length of a regular exam or one extra. Once again, first problem going to be some true or false stuff. I'll probably go with a little bit extra here. We usually do 5 of these, maybe I'll do 7 or 8. But just a few extra. And these will be basic theory questions. It'll be in neutral geometry, is this true? In elliptic geometry, is this true? And in hyperbolic geometry, is this true? So know your theory when it comes to each of the 3 geometries. Number 2, I really like the model building stuff. I think it's fun to sort of build models of finite geometries and see what you can come up with. So I'll just tell you right now, number 2 will definitely be one of those. It'll be model building. And this of course encompasses more than just build a model, right? It's build a model, are these axioms independent, and so on, right? So all of that stuff that we've done. 3, I haven't really tested you on anything to do with elliptic geometry. I suppose I could put in an elliptic proof. I'm not sure if I will though. But what I'll do is I'll at least make one of these short answer questions entirely elliptic stuff, right? So short answer, elliptic stuff. What do I mean by that? I mean, show me that you sort of understand the theory behind elliptic geometry, that you understand the difference between single elliptic geometry and double elliptic geometry, that you know what poles of lines are, that you know what the polar distance is, that you can define these things. So just the elliptic geometry stuff. 4, let's come back to, but 5 and 6, these are proofs. And these could be anything, right? Proofs from anything we've done this semester, neutral proofs, hyperbolic proofs, I suppose elliptic proofs. And then question 4, I haven't quite figured this one out yet. It'll either be a proof or some other short answer thing. It's some other theoretical stuff. Any questions? All right, well, I guess we're done then. Hope you guys enjoyed geometry too. And I'll see you Wednesday. Thanks.